My name is Wang Chen. I'm from Qingdao University. It's my honor to share the presentation. The title of my presentation is Controlling Opinion Dynamic and Consensus in a Social Network. Okay, I will introduce my paper from six parts, introduction, model, symmetric case with one player, symmetric case with two players, simulation, and conclusions. Uh, now let's begin. Uh, as we all know, in our life, there are so many societies. For example, all students in this classroom can form a society. If there is a question, how much time do you want to spend on studying after class? Different students have different answers. Some students think 1 hour, other students think 2 hours, so on. But some students can communicate with each other. We suppose these 4 students can communicate with each other. After communication, the answer of students will evolve. If there is a teacher, he hopes every student spend 1.5 past hour on studying. He will pursue some students, such as head boys or head girls. We suppose the teacher can pursue the boy. Then the boy will involve his answer, and he will communicate with these students. So the teacher can influence the answer of these students by pursuing the boy. In the society, we call students the agents and call teachers the player. However, it is significant for the society that all students in the classroom have the same answer to the question. Because if they have the same answer, the teacher can average their homework, and every student maybe think it's okay. Yeah, the society can be described by a social network. The social network is represented by a graph NE. N is the set of agents, E is the set of links. And if there is a link between agent I and agent G, they can communicate with each other and then can influence one another. However, the central applied by a player is an external central, which implies that the player can influence agents while agents can't influence the player. There are many such examples in our life. For example, the media can change people's opinions on some issues through reporting, but these opinions will not influence the media. Okay, from the example, we can get these conclusions. Firstly, in a society, every agent has his own opinion on some issue. Secondly, the player can influence the opinions of agents in the society by applying an external central to some agents. However, he should pay more cost for the centrals. Thirdly, agents' opinion can evolve due to communication with other agents and the influence of some external central. Fourthly, the goal of control is to make the final opinion of all agents as close to a desired one as possible with minimum control costs. Finally, if opinion of all agents are same, the consensus can be reached. The problem can be characterized by a game theoretic model of external central influence on opinion dynamics. Players can influence definite agents in the social network. Further consideration rests on the assumption that each player can influence only one definite agent. The dynamic game under consideration belongs to the class of linear quadratic games in discrete time. We try to calculate players' optimal central and analyze when the consensus can be reached or not. I will introduce the model. N is the set of agents and M is the set of players. Xt is a vector, its element xit represents the opinion of agent I at time t. AI is a coefficient and characterize player I. Xm is the target opinion of player M. Gamma M is the player M's cost of pursuit of influence intents. UM is a control of the player M. SI is a set of agents linked to agent I in the social network. Let's say SI is the set of neighbors of agent I. MI is the set of players influencing agent I. If no player influences the agent I, the MI is unempty. The opinion of agent I involves in this function. This function implies that the agent's opinion depends on two factors. This is the influence of surrounding agents, and this is the influence of different players. This function is the payoff function of player M. The payoff function consists of two components. The first, this one, reflecting the deviation from the opinion of all agents from his target value, and the second, this one is the control cost. Now we study a special case in which all agents are identical and communication with each other through a complete game. So the opinion dynamic in this model can be rewritten this form. Now we consider a symmetric case in which there is a player and he influence for the first agent. So the agent's opinion dynamics is the form as equation 1, in which x1 t plus 1 equal x bar t plus ut, because we suppose the player influences the first agent. For other agents, xit plus 1 equal x bar t. X bar t is a mean opinion of all agents. From equation 1 and x bar t, we can get the dynamics of x bar t. X bar t is the form as equation 2. This is the P function of player. That the dynamic game under consideration belongs to the class of linear quadratic games in discrete time. Optimal central is calculated using the Bellman equation. We can get the Bellman equation for this problem is this function. This part is the P function, yeah, and x t plus 1 satisfy equation 1. It's the dynamics. Then find a solution of Bellman equation in the form substitute x it plus 1 and x bar t plus 1, we can get v t plus 1 and x t plus 1. Yeah, substitute this function to Bellman function, we can get the optimal control. Ut is this form, and in which A and K satisfy the equation 4 and equation 5. Substitute ut to the dynamic of x bar, we can get equation 6. X bar t plus 1 equal x bar t plus ut minus ut over n. This function is ut. Suppose that optimal trajectory has a limit value x star under t tends to infinity. Let's see in equation 6, x bar t plus 1 and x bar t all equal to x star. Equation 6 is equation respect to x star. Then we can get the solution of x star. X star equal minus k over a plus n. From equation 4 and 5, we can find this relation between a and k. A and k satisfy k equal minus a plus n times x hat. Substitute this equation to x star, we can get x star equal x hat. It means that optimal central gives a consensus that consists with the target value x hat. So we can rewrite the dynamic equation 6. In this equation, we substitute this equation key to this equation 6. We can get equation 7. Now we consider a symmetric case where there are two players, and we suppose a player influences agent 1 and another player influences agent 2. So the dynamic of the game is this form, in which x1 equal x bar plus u1, x2 equal x bar plus u2, and for other agents, xi equal x bar. X bar is also a mean opinion of all agents, and u1 is the control of player 1, u2 is the control of player 2. From equation 8 and x bar, we can get the dynamic of x bar. Yeah, this equation is the P of functions of player 1 and player 2. Let us try to find a feedback Nash equilibrium of the above game. Firstly, we suppose player 2 choose control u2, and we can get the Bellman equation of player 1 as this form. We can use the same method to calculate the optimal central. Then we can get the optimal central of player 1 is the form as equation 11, in which A1 and K1 satisfy equation 12. From equation 12, we can see A1 depends on gamma 1. Yeah. Then we consider player 2's central problem. We suppose player 1 chooses the central u1, and we can get the optimal central of u2. U2 is this function similar to u1, and in this function we can get A2 and K2 satisfied equation 14, and A2 depends on gamma 2. From equation U2 and U1, we can rewrite U2 and U1 and U2 as this form, in which alpha I and beta I satisfy equation 5. Then this is system equations respect U1 and U2. Then we can get the solution of U1 and U2 as the form equation 16. Substitute U1 equation 16 U1 star and U2 star to the dynamic of x bar. We can get the optimal trajectory of mean opinion has form equation 7. Now we consider the optimal trajectory has a limit value x star under t tends to infinity. Then x bar t plus 1 and x bar t all equal to x star. Equation 17 is an equation respect to x star. Then we can get the solution of x star. It has the form equation 18. In this equation, if gamma 1 equal gamma 2, we can get A1 equal A2 and alpha 1 equal alpha 2, beta 1 equal beta 2. So it yields that x star is a mean value of targets of players. Now we consider a simple 3-agent scheme. We obtain numerical results that allow to analyze the convergence of opinions of agents, as well as the relationship of the remaining parameters of the model with each other. First of all, we consider a problem with a player who influences the first agent, and we suppose x0 equal 0.7.4, 0.4, and we suppose gamma equal to 0.01, delta equal to 0.95, and x hat is the target of player 1 is 1. The result can be showed in this table, and these two fingers. This finger is the optimal. This finger is the opinion of agents, and this finger is the optimal central of player. From this finger, we can see all agents' opinion is very close from t equal 10, and the optimal central tends to 0. So we get these conclusions. The consensus can be reached, and the limit value is player's target is 1. The control of a player is decreasing respect to t, and optimal control tends to 0 under t tends to infinity. Then we consider a model with 2 players. We suppose that a player influences the first agent, and another player influences the second agent. In this model, we suppose gamma 1 equal gamma 2. We can get this results. This picture is also the opinion of agents, and the picture is also the optimal central. From this picture, we can see the consensus can't be reached, and from this picture, we can see the optimal control doesn't tend to 0. So we get these conclusions. When there are two players in the society and their targets are different, we can notice that the limit opinion of agents are different, which implies that the consensus can't be reached. The optimal control tends to not 0 but a non-zero constant, because the difference between two players' goal leads them to apply control to offset the influence of another player. Finally, we consider a game in which there are two players, and two players have different course of pursuit of influence intents. Gamma 1, in which gamma 1 equal 0.01 and gamma 2 equal 0.03. We can get this results. Compare this results with last results. We can get in last results, the target of player 1 is 1. The target of player 2 is 0.6, and the limit value of X bar is 0.8. It is a mean value of player targets, but in this result we can see the value, the limit value of X bar is 0.778. Yeah. So we get this conclusion. When gamma 1 equal gamma 2, we can get X star is the mean value of player targets. And when gamma 2 doesn't equal to gamma 1, gamma 1 doesn't equal to gamma 2, then X star is not the mean value of player targets. This paper consider a game theoretic model of external central influence on opinion dynamics and reached consensus in a social network. In the special case where all agents are identical and communicate with each other through a complete graph, we can use the Bellman equation to calculate the optimal control, and the solution is constructed analytically. Finally, I want to thank Professor Mazalov and Professor Go. They give me huge help. Thank you, everyone. That's all.
Thank you very much. Thank you. Anyone has any questions? If no one has any questions, I have a question about the opinion dynamics, actually, because recently I have found a paper about the opinion dynamics and Bayesian updating of the opinions. I have a question. Do you have any plans to work on the Bayesian updating direction for the dynamics, or are you interested in this or not? Because yeah, just a question.
Yeah. I do mean
so I'm not a specialist in the opinion dynamics. I just studied a paper because I need to understand how the Bayesian updating is organized in the game, and in order to apply to the continuous updating. So, but anyway, I'm just interested whether you know this and whether you think that this direction of Bayesian updating in opinion dynamics is important. Because if it's important and you plan to do it, maybe we could collaborate on this in future. If you
cooperate, yeah,
Yep.
I think, yeah, I think that's a good idea, and I will consider it. Do you,
that's great, but okay, maybe I ask Professor Mazalov. Professor Mazalov, do you think that Bayesian updating for opinion dynamics is a kind of state of art approach or not? And did you work on this or not?
Yes, of course it's possible, but we don't think about it. We can apply it because it is the linear quadratic game, so we can apply updating also.
Okay. I just wanted to know if it's kind of state of art and it's important. Okay. Thank you very much.
Some comments that here it is important to find consensus. So the limit value of trajectories, and if to make updating, maybe they will not go to consensus. It is interesting from methodological points. I think we can think about it. Yes.
Maybe I could send you the paper that I have studied, because there also the authors, they studied the consensus with Bayesian updating. What happens when how the opinions converge, because they update as well. And I'm not specializing in opinion dynamics. I just was very interested how to apply this Bayesian updating for continuous updating. But anyway, I already not I. Actually, it's a joint work with Wanjing Zhou. So if you're interested, maybe we could collaborate on this. That could be very great.
Okay, thank you.
Thank you very much.
thank you.
Anyone else has any more questions? Okay, then.